Professor Kim for inviting us. And also thank you very much for coming. So we have 4 lectures today. And in the first 2 lectures, I would like to talk about the Gelfand-Cetlin systems. And its Toric degenerations. And this is rather elementary part. And in the afternoon lectures, Nishino will talk about an application to discounting problem. And in particular, we see that we can see the computation of potential functions. So let me start the background of the first part. So we start with the definition of completely integrable system. So let M omega be a symplectic manifold. Of real dimension 2n. Then a completely integrable system, is a set of functions set of n functions on M such that maybe I should go such that these functions are Poisson commuting to each other. We also assume that these are functionally independent. This means that the derivative of these functions are linearly independent on an open-dense subset of n. And the Gelfand-Cetlin system is a completely integrable system on a flag manifold. But before go to the flag manifold, we have to recall the basic property of the completely integrable systems. So if we assume that the fiber of this map are compact, then Arnold and Liouville theorem says that how to say? So each connected component of a generic fiber is a Lagrangian torus. Here is an example. The typical example is the moment map on a toric variety. So we assume that X is a compact toric variety and defined over C complex numbers of complex dimension n. And we assume that X is equipped with a symplectic form, which is a Kähler form with invariant under the torus action. Kähler form. Then we can consider the moment map of the torus action. Moment map. This is, of course, the dual of the Lie algebra of the torus. This is a completely integrable system. Completely integrable system. And the property is that, I have to say, and the image of, I'm sorry, maybe this is X. And the image is a convex polytope called the momentum polytope. Moment polytope. I don't know. For example, if X is or CP, for example, then its map is just a triangle. Or if irreducible surface of degree 1, its image is something like this. And so on. And the property is that if we take a point in the polytope, then if it's in a k-dimensional phase, then its fiber is isotropic k-dimensional torus. This is the case of the toric variety. Sorry?
In this moment polytope is only for this example or for every complete system?
So in this case, this is moment map. So not necessarily. No.
Why is it called integral system? Could you explain why is it called integrable system?
I'm sorry?
The reason that people call it integrable system.
I see. So when we fix, if we choose one function among this function as a Hamiltonian, then this condition is equivalent to that these functions are first integral of the Hamiltonian system. That means a conservative of the Hamiltonian system. Okay. So in that sense, in this situation we have many first integrals, as many as possible. In that sense, this is called an integrable system. Is it?
Each function is the Hamiltonian function?
We can choose one of the functions as a Hamiltonian. But in our story, we don't specify which is the Hamiltonian.
Just one of them is Hamiltonian. Okay, so there is the first bracket.
Yeah. Okay. Yes.
Integrals are obtained by integration?
Yes.
So you did the integral?
Yes. So we see here that the toric variety is related to some polytope. This is a relation in symplectic geometry, and there is another relation between the toric variety and this polytope. This is a story in algebraic geometry. This is given by so-called monomial basis. So here we assume that the cohomology class of omega is integral. Then we can take a line bundle on X such that its first Chern class coincides with this symplectic form, the class of symplectic form.
What do you mean by high inverse P of isotropic TK? What is that? Isotropic TK?
Isotropic means that the restriction of symplectic form to this fiber is 0. And maybe the simplest example is the case of CP1. In the CP1 case, the image of the moment map is just an interval. And if you take a point in the interior, then this fiber is a circle. This is a one-dimensional torus. And in the boundary, this is the point. This is a zero-dimensional torus. And in this case, so this part is the same as this one. So on the one-dimensional face, its fiber is a one-dimensional torus, and so on. This is the general situation for toric varieties. So we now go back to this algebraic geometric setting. Then we can take a line bundle, complex line bundle, whose curvature is given by this symplectic form. So this means that, so this is holomorphic line bundle, and ample in algebraic geometric term, or positive in differential geometric term line bundle. And what we want to, we are interested in is the space of holomorphic sections of L. Then this has a special basis. So if now X is a toric variety, then it contains a large, orbit of this torus, open orbit. Then we write so the coordinate of this torus is written by Z1 to Zn coordinate. Then, so this space has a special basis. So alpha is a point in the polytope, an integral point of the polytope. So here, G alpha. So if alpha is A1 to n, then Z alpha is defined to be Z1 to the A1 times Zn to Zn. So this is another relation. So in other words, the space of a homomorphic section has dimension equal to the number of integral points in this polytope.
Is that isomorphism canonical?
Yeah, this is just a so weight decomposition of the torus action on this space. This is just a weight vector.
I see.
So in the toric case, we have two relations. First one is a moment map, and the other is monomial basis. And in the flag variety, for flag varieties, there are also very similar relations.
When you talk about moment map,
Yes.
there's an ambiguity, right? You can translate.
Yes. So the ambiguity of translation is related to the choice of this coordinate. We can just multiply these coordinates by some non-zero numbers. Then I'm sorry. So right. Yeah, but it just corresponds to the choice of this coordinate.
Sorry, what happens in the case of CP1?
CP1, and in this, okay. So before that, CP1 case. Then, so, and we assume that omega is, so, let me, k times the Fubini study form. Then this line bundle is just k tensor power of the hyperplane bundle. And the space of this homomorphic sections on this line bundle is just a space of so monomials polynomials of degree less than or equal to k. So a polynomial in Z and so CP1. So for example, we use such kind of coordinate. Then this space is identified with the polynomial in Z of degree less than or equal to k, and it has a basis Z to 0, Z to right, Z to D, k. This corresponds to the so I is just a this is just an integral point of interval 0, k. This is the situation for P. And then we go to the flag case. So flagman, right? flag manifold is defined by maybe in general GLMC divided by some parabolic group, subgroup, or unitary group divided by some subgroup. Or you may just consider the case of full flag manifolds. B is alpha triangular. Matrices and divided by its maximum torus, diagonal matrices. Then, and we fix data. Then we have the similar relations. So we can then we can construct a symplectic form called a constant Kirillov form. I will explain this later. And line bundle if all lambda I are integral, and we can construct a moment polytope like a momentum polytope. This is called a Gelfand-Cetlin polytope. And there is a similar relation. So first one is the original work of by Gelfand-Cetlin. This corresponds to this situation. So Gelfand-Cetlin basis. So this is a basis of the space of holomorphic sections. And by Borel-Weil theory, this is the space of, this is a representation space of this unitary group, irreducible representation. This is the basis of the irreducible representation. The basis is labeled by the integral point of this polytope. Okay, N is the dimension of F. It looks the same. And Gelfand-Cetlin system. This is a completely integrable system on the flag manifolds. And its image.
Could you explain how you represent it? Could you explain how you represent flag manifold to a space?
Okay, so this has a natural action of unitary group. Okay, then. This,
first you represent group.
Yes. Yeah. Then this is a UN equivalent line bundle.
Right.
Then we can obtain the action of unitary group on this page.
Then the equivalence gives the relation somehow. The
relation?
equivalence gives the relation.
Relation with what?
Relation. So you represent this So then, but there has to be generator and there has to be relation, right?
I'm sorry?
So in a group, you
Yeah.
you get a generator and a relation, you get a representation.
Yeah.
So UN maybe as a group you can get a generators,
Yeah.
and then maybe the equivalent line bundles maybe that gives the relation.
This is one answer to that question. So this is the generator at the basis of the, and we can write down the action of the integral. So
what's the role of lambda?
lambda. This is so I'll explain later, but this corresponds to the highest weight vectors. I'm sorry, highest weight of the representation. I'll explain later. So then there is a completely integrable system on a flag manifold, and its image is coincide with this polytope. So the relation is completely parallel. And in both cases, we don't have big torus action a priori, at least. So we have only maximal torus action. This is much smaller than the dimension of the flag manifolds. So this does not give a completely integrable system. And also, the maximal torus action gives a weight decomposition, but the decomposition is not multiplicity free. So this does not give the basis. And the common idea, is just consider the chain of subgroups. And we consider the action of these smaller unitary groups. And there is one more relation. Toric degeneration. So namely, if degenerates into a toric variety x0, which corresponds to this polytope. So the moment polytope of this toric variety is this Gelfand-Cetlin polytope. So we just call this Gelfand-Cetlin toric variety. So we have these three relations in this case.
Suppose we scale, right?
Yeah.
Three will be scale.
Yeah.
So for those two, first
Yes.
two, so you're gonna find some big cross section on black variety.
Yes.
Such that the second one becomes a moment map.
Yes.
Right.
Yes. Right.
And then
But this is
using that action, you can decompose that representation space of.
But this is not true because the torus action is not holomorphic, so it drifts to this line bundle. So the idea is the same, but the relation is not so direct. So
there's no representation.
okay, so I will explain it. So this we can think of this as some weight decomposition of some commutative some action of some commutative algebra, but the action of commutative algebra is not come from the action on this space. So, and I think it is natural to ask the relation with these two structures and the corresponding structure on this toric writing. And Koga and Millap shows that the Gelfand-Cetlin basis can be deformed into monomial basis on this on these toric rights. And the goal of this morning lectures is to consider this side, to construct the deformation of Gelfand-Cetlin system into the moment map of x0. This is the goal of this morning lectures. So next we recall the definition of flag manifolds and then give the definition of this Gelfand-Cetlin system. So in this lecture, we just consider just only full flag manifolds. This is just for simplicity. We can easily extend the argument to all partial flag manifolds. Full flag manifold is a space of nested subspaces in fixed vector space Cn. The dimension decrease subspaces. The dimension decrease one by one. And as a homogeneous space, this can be written as UN over T. This is a maximal torus consisting of diagonal matrices. Or QLNC over B. This is a Borel group of upper triangular matrices. Its complex dimension is given by this.
You didn't write the dimension, right?
This one? Sorry.
The dimension, is it always one?
I'm sorry. This is K. Thank you very much. We use two other description of flag manifolds. First one is Yuichi embedding. So we set P sub k to be the space projective space of case tensor product of Cn. Then the flag manifolds can be embedded into the product of these projective spaces. So using this description, when we think of this point as a chain of subspaces, then we take it, the maximal wedge product of each subspace. We get an embedding into the product of this projective space. This is embedding, but for our purpose, we need the expression using coordinate called the Yuichi coordinate. So we take a point in the GL in C, and I to is I is a subset of the set of 1 to n. Then we define P sub I of Z to be the determinant of submatrix of Z given by I moves I1 to Ik, and J is 1 from K. This K by K small matrix, take small matrix, then it's take determinant. This is the definition of Pi. Then using these functions, we can write this Yuichi embedding as follows. So we call iota. Iota to the product of projective space. So this part is a homogeneous coordinate on this pk. So these pi are called the Yuichi coordinate. This is one realization of flag manifolds. And another description is co-adjoint orbital or adjoint orbital. So here we identify the dual of the algebra UN with the space of Hermitian matrices by the invariant inner product. Then we consider it as a joint orbit in this space. So we fix a diagonal matrix lambda 1 to lambda n, and these components are distinct to each other. And we define O lambda to be the space of n by n Hermitian matrices with fixed eigenvalues, lambda 1 to lambda n. This is the adjoint orbit of lambda by the action of unitary group on this space.
What's the relationship between this spherical coordinate and
Yes.
Planck manifold itself?
I'm sorry.
So what's the relationship between this Planck manifold and this spherical coordinate?
So this is a function on this GLNC. So this is invariant under the unipotent group of this action. So this map is well defined.
Okay, so the matrix G
yes.
represent a point in the Planck manifold.
Yes.
Up to P action P.
Yes. So this is this represents a class of Planck manifold,
And you can assign a lot of numbers.
Yeah.
That's defined up to scaling.
Yes. So as a homogeneous coordinate, this map is well defined.
I see.
This gives the map into this. So and then we go back to this coadjoint orbit. And then we can identify UN over T with this orbit space. But just take G T is identified with G lambda G star. Then so on this space there is a natural symplectic structure called the constant Kirillov form. Denoted by omega lambda. Take a point x in O lambda and consider its tangent space at x. Then the tangent vector at x can be represented as a joint of some. The tangent vector have the form this form. There is a vector in the Lie algebra of UN. Then omega lambda is defined by pairing of x and bracket of xi and eta. But for our notation, we put 2 pi over 1 here. Then this is, from this part, this is alternative. And we can check that this is non-degenerate on each adjoint orbit. And this gives a symplectic form. So, but we can express this using this Pruka embedding in terms of Pruka embedding. This form can be expressed as lambda k minus lambda k plus 1. This is a Fubini study form on pk. Of course, restrict to the flat manifold. This is a constant Kirchhoff form. Then we can give a definition of Gelfand-Cetlin systems. So in here we think of flat manifold as a co-adjoint orbit O lambda. We take point O lambda in O lambda. Then we define xk to be the space of the submatrix of upper left k by k corner. Matrix of X. Then xk is again a Hermitian matrix. So this has real eigenvalues. This lambda k1 of X. Lambda k of X. So we can think of this as a function on this space. Then we have a set of functions. K I k is 1 from n minus 1 and I is 1, 2. We have a function, the set of functions. The number of this function is just this number. This is the complex dimension of flat manifold. And the theorem is that Clemens-Stambard theorem is that this is a completely integrable system. This is the Gelfand-Cetlin system. I don't have time to give a complete proof, so just I will mention about the key idea of the proof. This is very simple. So we think of the small smaller size of unitary group as a subgroup of UN by UK n minus k. We embed the UK into UN in this way. Then the map X to taking its upper left corner is a moment map of this UK action on this O lambda. Then the theorem follows from the two properties. So if we take two functions on the image of moment map. Lambda I, I'm sorry.
Xk is a moment map of this.
Moment map of the action of unitary action on this symplectic manifold. So this.
Xk is a matrix.
So this is considered in Hermitian matrix of size k by k. This can be considered as identified with the dual of UK. And this is a point in O lambda. And this is a moment map of this action. Then if we take two functions on the image of the moment map, then I write this map by mu k. This is a function on this O lambda. And we can take a Poisson bracket. This is the same as the pullback of Poisson bracket. Okay, dual. So this is a Poisson bracket. Poisson bracket on find on each coadjoint of it. So given by this form. This is the first property. And another property we need is that this function is a pullback of UK invariant function on UK dual. This is just taking eigenvalues, so this is invariant under a joint action. This means that this function is constant on each coadjoint of it. So from this property, constant if this function is constant on each coadjoint of it, this Poisson bracket vanishes. So this also vanishes. This is the story of the proof. Let me show you a simple example. The case of n equals 3. In this case, the flag manifold has complex dimension 3. Then the Gelfand-Cetlin system consists of three functions. And its moment, its image, Gelfand-Cetlin polytope, has the form like this. So this is lambda 2, 1, lambda 2, 2, and lambda 1, 1. This is Gelfand-Cetlin polytope for three-dimensional flag manifold. The structure of the fibers are very similar to the toric case. Let's see. As the toric case. Almost everywhere. The only difference appears at this vertex. The fiber of this vertex is a Lagrangian three-sphere. This is only the difference. Except this vertex, all the fibers are torus. And let me explain more about the geometry. So let me draw a picture again. So in the toric case, the inverse image of each edge is CP1. But in this case, the inverse image of this edge is not a sphere, just a part of a sphere. If we take a union of these two edges, then its inverse image is a sphere. And the same is true for these two edges. Union of these two edges, its inverse image is also a sphere. And here, the image is, I don't know how to write it, so Lagrangian is 3. If we write the sphere as in C2, then these two spheres and the three sphere and one sphere, two spheres intersect at, for example, z is equal to 0. And the intersection of these two are given by w is equal to 0. So that in flat manifold, these two spheres does not intersect. And so in the next talk, I will talk about the toric degeneration. Then in this three-dimensional flat manifold, so the toric degeneration is given by shrinking this sphere into a point. Then these two spheres split into two small spheres. This is a rough picture of the toric degeneration in three-dimensional case. Maybe.
And the whole S3 connected?
S3?
Whole S3 booster point?
Yes.
So how can they intersect? Inverse image straight line.
Oh,
How they can intersect here?
these two, for example, so
The fibers are straight line.
So this So intersection of this one and z is equal to 0 is this one.
Intersection of the middle three sphere is the inverse image of the point, right?
Point of this
Vertex?
Vertex point.
vertex. This one and this one.
The middle three sphere.
And
Inverse image of the vertex point, right?
yeah, this is the vertex of inverse.
Upper three sphere is the inverse image of two.
These two lines.
Containing the vertex or just excluding the
No. I'm sorry. So this is not 3. So take open part and take inverse image and closure. Yes, right. So maybe I stop here now and take a break.